All right, in this video, we're going to talk about inclusive and mutually exclusive events. So let's start with an example of mutually exclusive events, which, as you can see, are events that cannot occur at the same time. So this first example says, let's let event A roll an even number on a standard six-sided die. So I'm going to draw a Venn diagram. Event A would be rolling a 2, 4, or 6. Event B is rolling a 3. So you can see pretty quickly there's no overlap between these two events. And now I'll go and draw the universal set around them. Universal set also includes the number 1 and the number 5. So the question wants to know, what is the probability of A or B, one or the other? This is the same as asking the probability of A union B. And a union, remember, means every single number that's a total of those two circles combined. So you have 1, 2, 3 numbers in event A, 1 number in event B. So the union of those two would be 4 out of a total 6 possibilities, since there's 6 sides to a die, and that reduces to 2/3. The question next is, are these events mutually exclusive? Can these events occur at the same time, or can they not? Well, you cannot roll an even number and get a 3 on one roll. So these events are mutually exclusive because they cannot occur at the exact same time. And you'll see anytime we have mutually exclusive events, really all we did was add the total possible outcomes for event A to the total possible outcomes for event B. There were 3 here and there was 1 here. 3 plus 1 gives us 4. It's kind of a shortcut way of doing it if you don't want to draw out the Venn diagram for every example. We'll get to that formula here in just a second. Next up is inclusive events. So this next example, we're going to talk about inclusive events. We've got different events. So let's go and redraw the Venn diagram. Event A is rolling an even number. So that's a 2, 4, and 6. Event C is rolling a number that is prime. So prime numbers from 1 to 6 would be 2, 3, and 5. But both of these circles have 2 in common. So the only number we don't have up there is 1. Some people make a case for 1 being a prime. We're going to assume it's not prime in this particular example. So now the question wants us to find the probability of A or C. Or again, it's the probability of A union C. So we're going to add up everything that's in A and everything that's in C, except you've got 1, 2, 3 numbers in A, and you've got 1, 2, 3 numbers in C, but one of those numbers, we don't want to count it twice, because it can only occur one time. So even though technically we underlined 6 numbers there, 2 we don't count twice. So there's actually only 5 numbers out of 6. That should make sense, because if we said 6 out of 6, then that means there's a 100% chance that you would roll an even number or roll a number that's prime, and we've established that 1 is neither one of those things. So there's a 5 out of 6 chance of event A or event C occurring. The formula to this is pretty similar to the previous example. You have to subtract, though, the intersection, the probability of A and C from the probability of, from the sum of the probability of A and C. So that intersection value just has to be subtracted from the sum at the end. And you can see here the formula is written down below. And then we're going to use those in the rest of these problems. All right, so example 1, we're looking at a survey about change in public policy. 100 people were asked if they favor change, oppose the change, or have no opinion about the change. So we've got a table here below. Let's determine if these examples are mutually exclusive or inclusive, and then determine the probability. So this first example says, find the probability that a randomly selected respondent to the survey opposes or has no opinion about the change in policy. So the first thing you'll notice there, it doesn't really talk about gender in this problem. So the columns referencing men and women, we can factor out in just this first example. We're just going to focus on this last column for this problem here. The question says we want to find the probability if they oppose or have no opinion. So I'm going to write the problem out like that. And then, is this an example of mutually exclusive or inclusive events? Think to yourself just for a second. And if you said these are mutually exclusive events, you're right. Because you can't oppose the policy and have no opinion at the exact same time. There's no overlap between these two classes of people. So even though the problem technically didn't ask us to determine if it was mutually exclusive or not, that tells us which formula we're going to use here. So since it's mutually exclusive, we're going to use this formula right here, where we simply just add the probabilities together. It's pretty straightforward when there's no overlap. So the probability of someone opposing is there's 37 people opposing out of 100 total respondents, plus the probability of someone having no opinion is 36 out of 100. Add those together. I think we're going to get a fraction that does not reduce. So there's a 73 out of 100 chance that one or the other occurs. Example 2, we want to find the probability that a randomly selected respondent to a survey is a man or opposes the change in policy. So that opens up the entire table here, since now we are talking about men, are focusing on gender here. And first we want to determine, is this inclusive or mutually exclusive? The probability that a randomly selected respondent to a survey is a man or opposes change in policy. So I'm going to write out the problem like this. Think to yourself, is this mutually exclusive or inclusive? If you said this was inclusive, you are correct, and hopefully you knew that by the logic and not because we've already done a mutually exclusive problem. But technically, someone can be a man and they can also oppose policy. So there's going to be some overlap here in our Venn diagram. So since this is inclusive, let's go back and let's look at the formula. The formula when it's inclusive, here, bear with me, down here at the bottom, we're going to add the probabilities together just like we did for mutually exclusive, but then we're going to subtract where they intersect. So first, let's calculate what's the probability of a randomly selected respondent being a man. Well, there's 50 total men, and there's 50 total women, so there's a 50 out of 100 chance of it being a man. And we're going to add to that the probability of randomly selecting someone that opposes. And there are 37 people out of 100 that oppose. Remember, that 37 can include women as well. But now we're going to subtract where these two events intersect at. So if we look at our table, we want to find out how many men we have that also oppose public policy. You can see the table lines up right here at 12. There are 12 men that oppose this. So we're going to subtract where they intersect, which is 12 out of 100. So add and subtract those three probabilities, and that gives us the answer to this problem. This one's going to be a nice round number, 75 out of 100. So there's a 3 out of 4 chance of either a randomly selected participant being a man or being someone that opposes public policy. I encourage you to try example 3 on your own. Pause the video, and I'll go over it in just 1 second. So pretty similar to the last problem, this is an example of inclusive events, because there's going to be some overlap here. So you need to find the probability of a woman being randomly selected. That again is 50 out of 100. The probability of randomly selecting someone with no opinion is 36 out of 100. And then you need to subtract where these two events intersect at. And then we look up here at the table. Women that have no opinion about public policy, there are 16 of them. So that's where the minus 16 out of 100 is coming from. If the math is right, that is total probability is 70 out of 100, which reduces to 7 out of 10.